Hey everybody, Adam Savage in my cave with Alex and Andreas from Lumafield. Okay, for the uninitiated, what do you guys do?
Yeah, so we make industrial X-ray CT technology. Basically, the way I like to think about that, fancy digital X-ray camera that's 3D. It lets you see inside things. Pretty much anything you put in the scanner. And then we make really powerful software that lets you analyze, quantify, understand what you put in the scanner, whether that's a golf ball, a battery, a medical device, a plastic bottle, and really understand what you've made, because it's always a little bit different than what you had in mind.
Well, and this is technology that we're used to, I think, culturally in medicine. But
exactly.
You guys have built a business-to-business application for it. And a couple of years ago, we went and looked at some cables. That was a fascinating dive into how much difference there can be in manufacturing tolerances and executions for what seemed like the same exact part.
Exactly.
And now we're here to talk about this. This is very exciting. So tell me about what's going on here.
Yeah, so Lumafield's first product was the Neptune, and that was really more for R&D and failure analysis. But we've moved to create solutions that also support production.
Okay.
And since we can scan now thousands of things, we had the idea, like, why don't we scan 1,000 batteries, right? Batteries are everywhere. I believe 10 billion batteries roughly are manufactured every single year.
10 billion?
Yeah, and 5 billion of them actually are in this form factor, the 18650.
And I have at least 1 million different kinds of these in a drawer.
Well, and you're, I think, a unique case. Most consumers don't interact with them directly. But like if you buy, say, like a cordless vacuum or a power drill, like they're actually just filled with these batteries inside.
And they gang them up into different form factors, solder them together to make different voltages.
Exactly. So we thought, why don't we take this standard form factor? They all look the same on the outside. That's what they're supposed to do. And scan 100 each from 10 different brands, so over 1,000 batteries total. Let's just see like what we can find inside.
So you're scanning multiple batteries from the same production line as well?
Mm-hmm. Yeah, so we bought over roughly 100 from each brand.
Yeah. Okay, and the secret sauce we're talking about here is also these are lithium-ion batteries, and if poorly maintained or dropped or hit with a hammer, they can easily catch on fire. Lithium-ion battery fires are a real issue right now in the world as we're producing more and more of them. I'm curious what you learned and what you were. Let's talk about like the overarching things that you learned, and then get into some specifics.
Yeah. So we scanned 3 brands that were like OEM manufacturers. So these are well-known, reputable battery makers. Then we scanned 3 brands that were quote unquote like rewraps. So they are buying batteries from presumably a manufacturer, who knows where, and then they're putting their own branding on it. Like this is a good example. This is Vapcell, so they have put a coating on it and they're targeting vapors.
So all they're really making is a plastic sleeve, and they're buying the battery somewhere else.
Exactly.
Okay.
And then we scanned 4 brands that were like low cost / counterfeit. So I bought 2 brands off of Amazon and 2 brands off of Temu, and those were my ultra cheap, kind of exciting ones.
That's exactly where I would start.
And I think one can intuitively infer, right? The high-end, expensive batteries are going to be better than the low-end ones. But what surprised us was just how much worse they were.
How much worse the non-brand batteries were?
Correct. So they were like, there's some key quality metrics, but like 33 of the low-end batteries, so that's about 8% of the batteries we scanned in that category, had a really dangerous defect where the cathode actually overhangs the anode.
Was that, wait, 33 of the batteries had that one defect? Mm-hmm. And was that across different brands of the cheap batteries or across one production line?
Within each of the cheap batteries, they all had that defect, although some were worse than others.
Oh my gosh. What does that defect look like? You guys got,
yes.
You made a whole, I love this report. This is great.
And you can also download it, of course.
And this is the thing I find so magical about this, is being able to manipulate and look at stuff in real time where you're seeing all the way through it. All right, let's take a look at this defect.
So when you think about this kind of battery, it's manufactured with a winding process. So you've got your layers of anode, layers of cathode, there's a separator in between, and then it's like being wound around a coil to make this cylindrical form factor. That's why they're so economical. And you want to have the anode, the negative layer, overhanging the cathode by roughly about 0.5 millimeter to prevent lithium plating.
Okay.
Because you have these structures, dendrites that form that can pierce the separator and lead to shorts, or that can potentially lead to fires in some cases.
So this is a defect in which it can actively get worse over time without you knowing.
Yeah, this is one of the things that's really like fascinating about these cells. We see a little green cylinder, and inside, the engineering behind this, the attention to quality in some vendors is pretty astounding. But it's this really. I think of it as like multi-physics. There's chemistry, there's structure, there's mechanics, there's thermals, there's material science. But this is this kind of living thing that changes over time. You're driving chemistry inside the cell to produce that current. You're moving, lithium ions back and forth between those electrodes. And so what's really interesting is there are a lot of different ways to understand the structures inside a cell. There's both the chemistry, there's the actual structure, and then there's the performance. So they have to, be structural, particularly as we get into, say, using these in like electric vehicles. These actually kind of form almost like a honeycomb, like a composite core structure honeycomb.
Right.
So they have to, withstand load on the top. That means they have to all be manufactured to the same heights. They have to have, clean terminals on the end so that you can robotically laser weld them. All of this stuff, and that's just the can that holds this together. And then you get to the inside, and that's where quality control and having a tightly controlled process for manufacturing becomes incredibly important, because you don't have a way of measuring that. As soon as you seal the cap, and it's very similar to actually to kind of putting a cap on like a can of soda. You put a cap, crimp it on.
You lose all access.
You lose all access. All you can measure after that is you can measure its weight. You can hit it with some ultrasounds. You can measure the voltage, but that doesn't tell you structurally what's happening. And I think this is the really powerful thing about CT. Is like a medical CAT scanner, we can get inside and see, are there any things that are suspicious that we can't tell from the outside. And so that's a lot of what Alex's work with the battery report dug into.
So what does the defect physically look like here?
Yeah, so here we go. Okay. So there's two elements we looked at. There's anode overhang, which is what I talked about, the parts overhanging the correct amount. These are like good examples here.
Okay.
So you can see that the blue dots, that's where the anodes are. They're pretty even, right, how much they're above the red dots. And the other important thing is like both lines are really straight. So that indicates tight process controls. It's not telescoping during the production process.
So it's not wandering as they're trying to wind it up.
Yeah.
Right. Whereas here you see there's like the red dots are on top of the blue dots.
That's bad.
That's objectively very bad. Right? Some manufacturers might have different tolerances for this gap, but it definitely shouldn't be negative. And then I love this battery where you see like...
It's everywhere. And that could lead to all sorts of other unintended consequences as things are expanding and contracting.
Exactly. And so like when you first have the battery off the line and you test it, it might perform just fine. But these are really like lifetime risks. As you use the battery and those lithium ions move back and forth as they're charged and discharged, then it can build up into these dangerous structures.
Did you also actually cycle the batteries, like charge and discharge them and then scan them again?
So we have done a couple experiments to that effect.
And have you gotten to see movement or deterioration from those scans?
So a lot of the dendrite structures, they're actually like microscopic. So we're not able to realize them in CT. But there are certain features in batteries like, for example, a current interrupt device. So that's something that if the battery gets too hot, it can pop open to break the circuit.
So it's a little mechanical thing within there that has a structure that responds to heat and creates a barrier.
So we can see when we've overcharged batteries that actually like opens up.
Yeah,
but on the cheap cells, I'm assuming
they
that
don't
might
even have
not.
those.
No.
And this is one of the really interesting things that when we look at, we brought some show and tell here. We have the cylindrical cells that we used for the battery report that Alex ran, and then we have a lot of cells look more like this. This is a pouch cell, prismatic pouch cells. So instead of rolling up electrodes into kind of a cinnamon roll, they actually call it the jelly roll inside the cell here. Yeah, it's industry term of art. The jelly roll is that electrode assembly that has all those very delicate thin foils. We're talking about like 10 micron thick layers of copper, of aluminum, and then the electrochemically active coatings, and then you use an electrolyte to facilitate ion transfer across that membrane, charge, discharge. So you can organize those in many different ways. We brought an example of a 4680 cell, which is kind of the bigger brother.
I want a flashlight that runs on these.
You can get them. They pack a punch. These are seeing some adoption in particular like the EV space.
Sure.
Where we're also seeing adoption of more kind of larger pouch and prismatic cells, because you're able to get better heat extraction. Again, these are there's a lot going on inside a cell, and so one of the things that's really fascinating is so Alex was kind of highlighting with the CID, that interrupt device, there are a lot of safety features that are constructed into these cylindrical cells. There's a ton of engineering that goes into that very, very top, those like top few millimeters. You know, there are sealing features. There's a little tab weld to make sure we're getting the current out of the cell. And then there are these safety features to make sure that, you know, if the battery overheats, it actually stops current draw. It's a little like a circuit breaker, just like inside your house.
And this is all because the anodes and cathodes are all coexisting up there, and anything bad that happens up there, that's where the danger will propagate. Is that right?
Exactly. Yeah. There's both we have the current interrupt device, so that little kind of safety fuse in the system, and then there's also, you know, venting and pressure release features, you know, basically guarding against different dangerous states that the cell could be in.
I also want to just like illustrate here for the audience that like when we're talking about these safety features, it's like there's two things to do in building a battery. One is to make sure it outputs power, and that's all of these do that. But the second is that it does that safely over a long lifetime of extreme discharge and recharge. Yeah. So I'm curious what was the most egregious lack of anything but electrons going out that you've seen.
Gosh, you want to take a whack at that?
Tell me about the worst one.
Well, so probably my favorites
all
would be
these different shapes. Oh
the
my gosh.
Bankia and the So Cool. These are both, I believe, from Amazon. But so you can see this battery actually advertises itself as a 9,900 milliamp capacity, which is like physically impossible.
Right.
And then you look inside and it's mostly empty.
And it's not even to the specs of the other batteries that it says it beats.
Mm-hmm.
Yeah.
And of course, it's like completely empty up top. There's like no safety whatsoever up there.
Oh my gosh.
And then what I liked about the So Cool battery, that one is actually like a counterfeit, right? So the low-cost batteries, they're not pretending to be another brand. They're lying to you about their capability, but
they're not pretending to be some famous brand.
Exactly. But this So Cool battery, I call it So Cool because the storefront was called So Cool Christmas Surprise. But they were selling quote unquote like Samsung 30Q batteries. Yeah. And then you look at that, and actually the performance when you initially put it in to run the test, it's not that bad. But the tolerance is right. It's like literally like the ocean or something. And you look at the real Samsung and it's quite straight.
Has this made you more concerned, or are you like the Christmas scold of like, I'm going to get you guys all good batteries for those toys you got?
A little bit. So like when you look at like battery statistics, like when I started this report, I actually didn't expect to find any defects, right? Because you hear like 1 in a million batteries will experience a reliability failure. That's like an average. 1 in 40 million will experience like a catastrophic failure. Of course, like 10 billion batteries are manufactured a year. So it's actually quite a good amount of risk regardless, even for like 1 in a million. But we only scanned 1,000 batteries. What I really learned is that the risk in cells is not evenly distributed.
Yeah.
Right. I see. Right. So when you buy name brand ones, those aren't failing at 1 per 40 million. Those might be failing at a tiny fraction of that, and the rest is made up by Temu and Amazon.
Yeah. It's not the same.
650s.
It's not equivalent to, say, like, you know, name brand versus like generic Tylenol. It's actually quite a big difference that we're seeing because the pros, the OEMs. They're doing this at a scale and at a reliability with the quality systems. You know, a typical 18650 is made, you know, between 400 and 600 of these per minute. The manufacturing rates are astounding. And so in a fraction of a second, you have a winder just zip, creates that jelly roll, kicks it out, goes through QA, then, you know, many steps produce the cell that we actually see here, and after every step, there's QA in those OEM lines.
Right.
And what we see in the battery report is both a lack of the engineered safety features that you find in those OEM cells, as well as very strong indications of lack of proper quality control and process control to produce a reliable, safe product.
Your machine can see all the way inside of this and understand these batteries. I'm curious if you, I don't know, I'd love to have a checker where I could see if my battery at least had a safety cutoff device. Is such a thing even remotely possible?
I'm not familiar with one.
Okay, all right.
It's a real kind of technology team effort to understand and validate the quality of these cells.
Right.
You know, there's the chemistry, there's the thermals, there's the structure, there's ultrasonic testing is a pretty high throughput way to understand certain aspects of battery quality. But at the end of the day, for understanding the structure, looking at this cell and this cell from the outside, they are absolutely identical, same mass, to my highly calibrated hands here.
Yeah.
Put them on the surface plate, they're the same height. Pretty much every observable that we can get from the outside is the same. And, if we hit them with a multimeter, they're both going to read, on order of 3.6 volts. And so there really isn't a method other than CT or X-ray to actually understand that internal structure, to actually quantify it and make sure that it is within your nominal bounds.
And purchasing from your trusted brands.
Exactly. So this is one of the things that we see is, particularly in automotive, really in just kind of modern manufacturing, very few things are made under one roof anymore.
Right.
You have a network of suppliers. And we saw this during the pandemic, a lot of disruption, a lot of secondary supply, a lot of secondary sourcing, moving vendors very quickly. And so what often happens in these kind of product development processes where you have an OEM with a bunch of tier 1, 2 suppliers, if those vendors change anything or if their vendors change anything, those can be kind of silent changes that can get deep into a product before it actually anybody finds out. So we see this being used for kind of IQC, incoming quality control at OEMs to check, make sure that nothing has changed. Because again, the outsides can look exactly the same. They can have the same mass. They can have the same voltage, but you'd never know unless you check inside.
That's really scary.
A colleague of ours, his garage burned down due
What?
to...
Garage burned down?
Yeah, his garage burned down. He was charging some lithium-ion batteries in the garage, which, he's very careful about it.
Yeah.
But something happened at 4 a.m, dog was barking, garage was on fire, called the fire department. So, these things were never, that far removed from these. And particularly as we find more and more of these cells in, everyday devices, I've got, at least 4 or 5 on my person right now.
Right.
I think the typical American has...
Yeah, there's a study that the average American has 9 lithium-ion powered devices.
Okay, then I'm way outliers. I probably got 40.
You probably got 9 on you right now.
Yeah, exactly. So what does a consumer do? This is obviously you buy from reliable manufacturers, you buy from reliable vendors. What is a guiding axiom that a consumer can take away from this?
Yeah, ultimately, unfortunately, as consumers, we're so beholden to the device integrator to do the right thing because we don't have really the ability to take a look inside and verify or change the batteries on our own. So what we can do is just be critical of when you see something that looks like maybe too good a deal to be true. You might save a few dollars in the short run, but in the long term, you could have really devastating, super expensive consequences to that. And also be alert to the possibility that like all the devices you own, like all of them carry a little bit of risk that they could overheat or catch fire. So if you smell anything weird, anything seems warm, like immediately stop using it. If you're able to like put it outside to burn out, do that. If you're not able to fully submerge it in water, don't splash water on it. It'll make it worse, but like fully submerge it.
I'm curious why you started on this project. This is a really great bit of consumer information that is necessary, I think, to function as a society and as a culture. What was the impetus for starting this research?
Yeah, I think I've always been curious about batteries. The first battery piece I actually did at Lumafield was about the Anchor power bank recall, because that was a power bank I actually personally owned.
Oh, amazing.
And it started, and I took the scan and I didn't realize it's actually just 3 18650s inside. And it really like changed all, you see a battery pack, I've always just assumed it's like one thing. We have such a powerful tool at our disposal to be able to look inside and analyze the quality. And I think a lot of people have that curiosity. Every time you got an airplane, like make sure you don't check any lithium-ion batteries. There's warnings all the time everywhere, and people get sort of desensitized to it. But I wanted to do some research and really see, like, is there any way we can maybe prevent some of that in the future?
I'm curious, in your guys' outreach about battery technology, what is the industry response? You got a lot of attention for your Haribo scan, right? Tell me about this story.
Yeah, so again, looking at viral consumer products, this Haribo power bank went really popular on the internet for being the cheapest, like highest power bank on the market. It's like 20,000 milliamps, and it's like maybe $25, $30 or so. So
millions of people wanted to buy this.
Everyone wanted to buy this. It was really popular with like ultralight hikers, like really serious backpackers.
Oh yeah, okay, of course, yeah, people who need batteries in the field,
But unfortunately, the classic story of cheap is maybe too good to be true. We scanned it and found like really questionable edge alignment, really poor overhang. Basically, we didn't measure the capacity because especially once you kind of look at the layers, you don't really want to test it to its full capacity.
But you described like a whale tail in there. Is that the winding just like going completely off the rails?
Exactly. There's 2 pouches in there, and like the winding in those pouches is like extremely low quality. So you see like this like really undulating layer going on.
Okay, so you released that scan. What is the response?
It's actually got the power bank pulled from Amazon, but there's a whole product line of Haribo branded consumer electronics. There's like earbuds with a screen, earbuds without a screen. They're like $25 and $14 respectively.
Yeah.
There's charging cords. So we scanned the earbuds as well, and those were even worse.
In terms of their manufacturing quality and battery compromise?
This had the cathodes coming out above the anodes, which we talked about, and the cathodes were even splitting, like they were fraying.
Oh my God, that's terrifying. And you put this in your ears.
Exactly right. That's not a place you want a battery fire.
Okay, so at least the world can respond in a reasonable fashion when they have the information.
The earbuds are still up.
Oh, okay. Oh, shoot.
They haven't been as viral as the power bank, but it's just, again, a warning to consumers, right? Like if it's a really good deal, even if this is adorable, right? We were so disappointed to find they were low quality.
I love Haribo. Yeah, no, totally.
It's not worth it.
No, it is not worth it. Alex, Andreas, I really appreciate you walking me through this. I have dozens and dozens of these, and I think I'm going to throw a bunch of the ones that are unlabeled out. We're going to include, is the study available online?
It is.
We're going to include links to this in the description along with Lumafield's critical information. Guys, thank you so much. Buy good brands.
Buy safe brands.
Okay, thanks, guys. One of the most difficult things I have ever done in my life was write this book, which I did in 2018, released it in 2019. And I've been noticing as I do the cons and sign autographs, that a lot of people are bringing purchased copies of my book for me to sign. So we thought, let's make them available at adamsavage.com. This one was ordered by Zachary for his friend David for his birthday. Happy birthday. Oh, whoop. There we go. Everyone's different. AdamSavage.com.